Right, first of all, thank you very much for the kind invitation. I was scratching my head together with Gita. We were wondering, why are we here? But okay, let's see. Maybe you find it useful. So what I'm going to talk about, and I have to thank Peter for laying the foundation for this, is to use X-rays for investigating skyrmions. And I'm going to try to explain to you why I think that X-rays are superior, but of course you need all methodologies in conjunction to really decipher skyrmions and skyrmion phases. But there are some nice twists to X-rays in this context. I'm going to start with a quick introduction to winding numbers, and then talk about X-ray techniques, resonant elastic X-ray scattering and reflection transmission, then how to dissect skyrmions with something we call CD-REX. CD stands for circular dichroism. And then if I have time, which I won't, because it's an unknown format for me, it's either 10 minutes or 12 minutes, or it's 45 plus. So we'll see. I have to cut off. But my alarm is going off, so it's all going to be fine. Right, so what do I mean by dissecting skyrmions? So if you look at the length scale of a skyrmion lattice, so this is on the order of hundreds of microns to millimeters, then if you have a probe that is small enough, you can also measure skyrmion domains, so that are rotational domains of this hexagonally ordered system. You can zoom in and look at single domains. But then below that, below 100 nanometers, lies the world of winding numbers and helicities. So this is the flavor of the skyrmion, essentially. And what will be important in this analysis is to realize that you can represent a skyrmion in this triple Q model or construction. So you can think about the skyrmion lattice being composed of characteristic or base helices. Okay? And these have certain flavors like Néel domain walls and Bloch domain walls have. Okay, so let's go back to the basics for a moment, right? So if you look at the topology of a vector field, so you can represent that in physical space and then map it by stereographic projection onto order parameter space. So if you have this distribution of spins, you can map it onto order parameter space like so. Okay, and now you can look at nice symmetric objects. So one on the left here. So my pointer is no longer working for some reason. Okay, anyway, the one on the very left, that is one where the spins all point up. The next one is this hedgehog type thing. Then comes one where you have these equatorial moments, and then on the right, something knotted. That looks a bit interesting. So how can you actually classify these? And so in topology, you do smooth transformations. And what you will find is that if you try to comb this hairy ball here, so some of these objects on the right, the three on the right, then you will end up with a knot. So these are special in a way. Okay, so let's try to quantitatively characterize them. So if I take this nice equatorial object here, and I cut it and project it down again, then you have this beautiful spin helix in real space. Okay, and so the parameter to characterize it is what on the very first day was introduced by Marcus, is the topological winding number. So it's this integral here, which is 1 for this specific type of object. And if you do that for the ferromagnetic state, then you end up with a winding number of 0. So that is trivial in this case. And this more weird-looking one, that has precisely the winding number of 2. So it's like a higher order type of skyrmion. Okay, and so if you look in the real world, then on the left-hand side, you have your ferromagnetic state, and you, of course, have domains within it, fine, but within the domains, it's all ordered like that, and the winding number is 0. Skyrmions come basically in two flavors, or two extremes, Néel type and Bloch type skyrmions, and below is Lorentz TM images of these skyrmion types. On the right-hand side is Addisimo with a winding number of 2. Okay, so this is the mapping for the winding number 1. Let's see, oops. Okay, I got control again, right? So this is the mapping that you do on the right-hand side real space onto order parameter space. If I then do that for winding number 2 system, then this will mean that I have to go around twice in real space and map that onto order parameter space. Okay. Right, so let's look at the techniques, resonant elastic X-ray scattering. What we are using is an end station like this. So this is a big scattering chamber. Looks like a gigantic wagon wheel at a synchrotron facility where they can tune the X-ray wavelength, that means energy, but also the polarization. Okay, and so we are using soft X-rays because we are looking at 3D systems. And so the energy range is less than a kilo electron volt. The wavelength, therefore, then is between 1 and 3 nanometers. You can look at 3D systems, so at the L2, L3 edge, say, of iron. Or you also can look at the M4, 5 edges of rare earth systems. The measurements have to be done in UHV. It's not hard X-rays here. The soft X-rays are absorbed in the uppermost layers, so it's very surface sensitive, and they are polarized. On the right-hand side, you see here the undulators that are used, with which you can essentially create arbitrary linear polarization or circular polarization. Okay, and X-ray scattering is not something that you usually learn has anything to do with magnetism, because it is actually quite a weak effect compared to, say, neutrons as a probe. And so this has to do with the fact that we usually look at, on the left-hand side, Thomson scattering, which has no magnetic signature. You can look at non-resonant magnetic scattering. Again, it's a very low amplitude. And on the right-hand side, what we do, we tune the energy such that we excite a core level electron up to above the Fermi level. So it's a two-step process, and then the re-emission at the same energy is what we observe. And this is the expression for the resonant scattering form factor up to first order. And you see on the right-hand side this imaginary term that has this cross product of the polarizations of the scattered and incoming X-rays. And then you have the magnetization component dotted to it. So from a periodic lattice, in this case here, our fruit fly of Skyrmions, which is carboxyselenate, fantastic system, is shown here. So that is the sum over the copper sites in the unit cell. And you see here we get our scattering expression times the Fourier transform of the magnetic moment. Okay, wonderful. So how does that look like? Well, we need a synchrotron, we need a Skyrmion lattice, and what we get on a CCD camera is this diffraction image. So we have 6 spots from this hexagonal order of the lattice, and then we have a bright blob in the middle, which is the specular beam. And it's reflected. You see a dark line running vertically. That is a beam stop, such that the camera is not destroyed, because they're quite expensive and people have destroyed them quite often all the time. Right. In the bottom left-hand side, a little bit sort of hidden, is the so-called universal phase diagram of bulk Skyrmion systems of the B20 type, to which also carboxyselenate belongs in the behavior. So the high temperature Skyrmion phase, they found another one at low temperatures as well, is stabilized by thermal fluctuations, but it's just below the transition temperature. The ground state is the helical state. If you apply a field, you transition to the conical state and then into the Skyrmion pocket. Okay. Right, and so we can look at the various phases. On the left-hand side, there's the helical state. You see the 2 peaks that belong to that. In the middle is the conical state. This is aligned along the field direction. That is what you do in a conical system. And on the right-hand side, you have the Skyrmion state. And now I just put a big blob in the middle to blank out the thing there to enhance the contrast. But I shouldn't be lying. We have a problem in resonant elastic X-ray scattering, and that has to do with, well, the magnetic element that we want to look at. So I just said that carboxyselenate works beautifully, and the reason for that is that at the L3 edge, we have a wavelength of 1.3 nanometers, and we have a rather large unit cell of 8.9 angstroms. So therefore, we can reach a Bragg peak, a structural Bragg peak, and the incommensurate magnetic order is decorating itself as magnetic spots, it's magnetic satellites around this the structural peak. Whereas other famous materials, like it all started with manganese silicide and Christian Fleider's work with SENS, with small angle neutron scattering, that is inaccessible for us, okay? And so is iron germanium. Doesn't mean it doesn't work, but you have to bear that in mind for reflection measurements. Okay, the other thing that you can therefore do is to also do small angle scattering, but with X-rays. And what you need for that is, oh yeah, now I have something wonderful. What you need is a small lamella, and so this is fibbed, put onto a holder, and then we can look in transmission, and you can also get your 6-fold peak. This is now a lot dimmer because it's just less material to scatter from. But the cool thing is that we have an octopole magnet in which we can carry out this type of work that's shown on the right. POMS means the portable octopole magnet, and with that we can do fancy field histories. Maybe I have time to show you some results that were obtained with that system. But that does work as well. And there are more X-ray methods which I'm not going to cover. It's STIXM, so that's an X-ray microscopy technique. One of the best beam lines for that is in fact at Bessie, and I should also mention PSI, of course. They are online again, so I should not talk about that. Okay, then you can do holography, tachography, laminography. So there is a whole bunch of methods with which you can study these magnetic systems with X-rays. Okay, so let's dissect the Skyrmions and look at the two features, topological winding number as well as chirality. Okay, so when we started with the field, there were, it was sort of a hard and fast rule. There are two types, Bloch-type Skyrmions and Yale-type Skyrmions, as you can see here on the left and on the right. But of course, you can, if you look at the equations here for the three magnetization components, you can see there's more stuff in there. There's the n, is the winding number, and the chi, and that is the helicity angle. And so the helicity angle for the Bloch-type Skyrmion is plus or minus 90 degrees, where it is 0 or 184 Néel. But it's a really continuous quantity, as we found out. Okay, so to unlock all of these secrets, we actually combined X-ray magnetic circular dichroism, where we use right and left circular polarized light to do this resonant absorption, which was covered again by Peter on the first day. And then in the setup, in the setup we can also, so that's the left and right circular polarized light. We can also look or do scattering with linearly polarized light, so it's either P or sigma, but in our case the annulator allows us to continuously change the polarization angle as well. The other degree of freedom we need, this is our sample, so Ki, Ks define the scattering plane, is the rotation of the sample about Q, the scattering vector, and that's the angle psi. So if you have all of that, you can get going. And as I mentioned on the first slide, right, if you think about the triple Q model, you can think about Skyrmions first of all as general types of spin spirals, okay? And so the question is, how can you characterize these spin spirals? And top left is an example of a transverse helix or cycloid. This is a proper screw. And what I showed is, so in green, this is what I call the common rotation plane, and then this plane can be somehow oriented in space. And so the helicity angle for the thing on the top is 0 degrees. If that is pointing towards you, that common rotation plane, it's 90 degrees, but it can have also values in between. So characterizing all of these is what you can do, in fact, but spirals are boring, so let's move on to the Skyrmions, okay? And they are the helicity angle. So how can you determine it? So if you do a scattering experiment of this spin spiral here with a helicity angle of 300 degrees, what you will find, if you look at the disordered spin helix system, is that you have the intensity distributed around a ring. This is what you would expect for plane scattering, but now we have two colors. One represents a positive dichroic signal, and the other one a negative dichroic signal. And there's a dividing line between that. So what this ICD really is, this expression here, is the intensity around the ring, where the angular parameter is psi. Okay, so this is the rotation of the sample. And what we get is the lambda, that's the magnetization orientation of the core of the skyrmion. Y is some function that is specific for the system you're scattering from. And then in the sign expression, you have the psi angle, that is your running parameter, and the phase shift, so to say, that is the helicity angle that you can get out of this expression. Okay, so this is an animation for a linear polarization. So we just look at the linear polarization vector rotating around. This gives us the x-axis in this plot. It's a polarization angle from 0 through 360. And what we do here is we look at the spin as it's moving from the plane to the out-of-plane direction. As you can see, the form factor is actually, or it's the absolute form factor is maximal if this angle is at 45 degrees. So if the spin is in plane or out of plane, the signal is 0, and if it points at 45 degrees, it's at a maximum. Okay, so now let's look at it as a function of the azimuthal angle. So these plots are now at, for the spin at 45 degrees, but rotated around the psi, and you can see that you get the phase shift here in these plots as a function of polarization angle. Okay, wonderful. So if we put this together, then this is what we get, in fact, for the Skyrmion lattice, now using, again, circular polarized light. And you can see here that there's a one-to-one correspondence between the helicity angle that now goes from Néel type to Bloch, was just at -90, back to Néel and back to Bloch again. And you can see that we call this the extinction vector. So it's the dividing line between, say, positive and negative diachroic contrast, right? So determining that allows us to determine the helicity angle in the system. Okay, so that's our Skyrmion clock. I actually made one for my student when the paper was out. Very nice. He had it in his kitchen ever since. Okay, so let's look now at CD Rex again as a function of, I think I have to start it by hand, as the helicity angle. And you can see that as a function of that, if we look at this plot of this diachroic intensity around the ring, then we can see that the helicity angle can be read off the zeros in this ICD curve. Okay. Good. And so now what happens if I rotate the sample, because this is a degree of freedom I can use for this. So if we are in the Bloch type Skyrmion, and if I rotate either the Skyrmion lattice or the sample, which is probably more practical, you can see that your six-fold pattern is, of course, rotating because your lattice is rotating underneath. But you can see that the dividing line, this extinction line between positive and negative contrast, so between blue and yellow, is actually staying fixed. Okay? So this is exactly what we are after here. Okay, and so the other thing that is important to determine is the winding number of the Skyrmion. And I will make an argument at the end of this section why I think that X-rays are really the best way for doing this. And just as a reminder, this is our scattering configuration, and I introduced a polarization angle. So this is beta, and this is for the linear polarized light. And that is with respect to sigma polarization, which is horizontal, and then turning that up 90 degrees would represent pi polarization. Okay. So in our expression for this dichroic intensity as a function of psi and now n, is that we see that the n is entering this equation as a prefactor to psi. So that means we just get higher order signs in this fit. And from that, we can determine n. The problem is this only works if n is odd. If n is even, this doesn't work, and the dichroic intensity is simply 0. However, if we now look at the intensity using linear polarized light, and now this beta enters, so this is the takeoff angle of the linear polarization with respect to sigma polarization, then we can see we have a little bit more complicated equations, but because we can vary beta continuously, we can obtain our n from this as well. Okay, so for a winding number 1 system, what we will obtain is a plot like this. So what is positive dichroic contrast, what is negative dichroic contrast, and we'll have these zero crossings of this line in the zigzag where we can read our helicity value from, and from the number of crossings we can get the winding number. It's just the number of zero crossings divided by 2. So this is for an n equals 1 system, and this is for a weird looking n equals 3 system, and you have equivalently 6 crossings. So 6 divided by 2 gives you a winding number of 3. Okay, that is the plot for that, and you see here the problem is the serious issue that, again, we don't see that for the n equals 2 system, but as I said, if we take into account beta as I introduced, then we end up with these polarization and isotropy maps, and you can see that also from this one here, you can nicely determine the winding number, also for even winding numbers. And it's the same argument again, so it's a plot. This is the psi axis, and this is the beta axis of the linear polarization. It's just the number of peaks divided by 2 gives you your winding number. Okay, so how does that work in reality? As I said, our problem in reflectivity is that we can only have the fruit fly to work with, really, because in forward scattering, we can't do this analysis. The amplitudes are just too small. And so looking at CSO, carboxyselenate, we actually find, so these are 3 scans for 3 different psis, and then we have this dichroic intensity plot. Now these are measured data points. We can extract from that our polarization and isotropy map looks like this. This is just a nice, more numerically improved version of the experimental data, but you can see clearly your 2 peaks. So it's an n equals 1 system as expected. Okay. Good. So I said I want to make an argument for X-rays. Again, think about it as a complementary method. If everyone would try to do X-ray scattering, I don't think there would be enough beamlines for that ever. So what I showed in the center is Lorentz TM, and that's sort of the method that was for the first time, seeing is believing, giving us real space images of skyrmions. So that was very nice. But there are a couple of catches with that. But the first problem, I would say, is that if you look at an n equals 0 system, so this is a so-called target skyrmion with a winding number of 0, on the right-hand side, it's a Néel-type skyrmion, Bloch-type skyrmion with n equals 1, then the LTM contrast for both is pretty similar, or I would say equal. They can play some tricks, but as skyrmion sizes shrink, I think that's probably why Christos wanted me to talk about. If the skyrmion sizes shrink, you have this resolution limit in all kind of microscopies, right? Maybe not with STM. If you really push it, if you think about this data from Hamburg, then I'm quite hopeful. But for many other methods, it would simply be not possible. Whereas with X-rays, you are sensitive to the sort of topological properties more of such base helices than you are with any other method. So we can still determine that. Okay, what is the other problem? The other problem is the fact that you work with lamella. And if I have time, I will quickly comment on that as well. Okay, good. So now that we dissected it, what we are really interested in these days, and I'm just going to give you 2 or 3 slides, is actually 3D skyrmions. Okay, and the way we do this is if you look at the sampling depth across the L2, L3 edges, you can see that it's varying. Okay, if you are at resonance, you are very shallow in your probing depth, sampling depth, because the X-rays are absorbed resonantly. If you're off edge, you still have plenty of photons. You actually have a larger sampling depth. So using that, we can actually look at the distribution of the helicity angle as a function of depth, and we can sort of do a layer model and reconstruct all of this and do a fit. And what we get out of this is this. So this is on the right-hand side, the measurement that we did across the L3 edge. And what we find is that, well, we never get the block type skyrmion that the system should have, but instead, if we are at resonance, we have a large angle close to 180 degrees, in fact, and a lower angle closer to 90 if we are probing deeper. Okay? And if you do a fit, and it's all, the only thing we require is that in the bulk it's 90 degrees, in the bulk it's a block type skyrmion. I think that's established. And the free parameter is the helicity angle on the surface, and that indeed is 180 degrees. So these block type systems have nail type skyrmions at the surface, which is important if you think about devices, right? Because this is probably not what you want. Or, well, it's on the other hand, on the right side, another parameter you could tune. So, out of time. Oh, right, okay. So let me just finish with, this is the surface twist reconstruction of these systems. What we are using this for now is to couple different skyrmionic systems. So we have systems in these non-centrosymmetric materials, and we couple them with heterostructures, where we can more freely design skyrmions and look at their mutual interaction. Okay, I think just one slide is important to conclude with, probably without going into any more detail, is the fact that if you work with lamella, and this is true for Lorentz TM, but also for X-ray techniques, is that the skyrmion pocket that is actually rather small in the bulk material is hugely expanded in lamella. The field values, the critical field values around the pocket, transition temperatures, everything changes. And that is a change in strain state, which is a really big caveat that you have to bear in mind. So I stole this plot from our previous skyrmion grant, EPSRC, where Gita and I were on. So I think she's also going to talk about things that were developed during that very nice funding time that we had. Okay, so I skip over the dynamics. That's another thing that we're doing, and just come to the conclusions. So I hope that we're able to convince you that skyrmions can be dissected with X-rays. We have access to winding number and helicity angles. And I just wanted to show you the publications in which we describe these methods in great detail, which you can read up on. And then I want to thank my expanded team from Diamond Light Source, where I'm across the appointee to, as well as ISIS, the neutron source, because we also do a little bit of neutrons, and a bunch of other people. Right, and if you look at it and you look for the future, I think the person that got it best is Richard Brereton, who went into Formula One. He sometimes sends me pictures illegally of the new versions of the race cars that they're modeling, so that's quite impressive. Anyway, thank you very much for your attention.